like the omega naught. Okay, somebody is recording them. Yeah, please. Thank you very much. I am recording the session as well. Okay, you're recording. Okay, thank you. Somebody recorded already. Will I be getting it or not? I don't know. So, yeah. So these the resonative frequency occurs at a particular peak, and on both sides it will be having less than the maximum power. So on both sides we'll have two frequencies at which the power is half of the maximum. We call that omega 1 and omega 2. For certain circuits, like generally it could be uh, uh, like it is possible to have uneven distribution. Like one, say suppose omega naught is suppose 100, omega 1 could be 95, and omega 2 could be 120. So on one side the difference is 5, and the other side the difference is 20. But for a circuit which is carefully designed, careful design means that we get a high Q, not IQ, high Q, which is the quality factor. In that case, we will get even distribution. So the shape of the curve is symmetric around omega naught. So omega naught, like omega 1 and omega 2, are evenly placed on each side of the circuit, the resonating frequency. The difference between omega 1 and omega 2 gives us the bandwidth. Bandwidth is sort of a range of frequencies between which the power remains between half and maximum. Remember, omega 1 and omega 2 are the frequencies at which the power is half of the maximum. So somewhere between is maximum. So between these two frequencies, the power remains between half and maximum. All right. So Q, and so the good thing about this is after understanding, we can make use of some formula. And if we see the formula, I should be able to. So this is basic definition. Yeah. Okay. So we're talking about the magnitude and phase when we're talking about the transfer function. Transfer function could be anything. It could be voltage upon voltage, or current upon voltage, or current upon voltage, or current upon current. It could be anything, but it has to be output or input. OI, OI, and OI should be output upon input. I don't need to see this thing. Can I move it? Cannot. Okay. I can go here probably. Okay. So finding the transfer function is nothing but relating the output and input. So relating the output and input is you just use basic circuit laws, and with those circuit laws you should be able to eliminate the unwanted variables and relate output and input, in this case VO over VS. Yep. All right, we had this messy slide just to show how to find it, and it's nothing but basic circuit law. Like this time is using VDR, and then relating VO over VS, finding the magnitude, finding the angle. So it's like complex. Don't worry about how it looks like. It's just a complex number. So just if you don't understand how we did this, just find the magnitude of that particular complex number. Simple as that. Just find the magnitude of this and then find the angle of this this complex number. You will get the magnitude and phase. Plotting the magnitude and phase for particular values of R and C, and later on R and L will have different values. So somehow it's good to define omega naught. Omega naught will be in this case 1 upon RC. So it's like omega upon omega naught. So this is in this case. And then what else? How to move forward? Yeah, we're done with this. Done with this. It's too messy. I will give you a clean one. Don't worry. So this is the clean one. Yeah, this is the clean one. So this is time around. This is the RL. So the previous one turned out to be a low pass filter. Low pass because low frequencies are passing and high frequencies are like sort of suppressed or blocked. RL circuit we did in a similar way. So we got, this is a clean one. So this is a high pass because low frequencies are blocked and high frequencies are let go. So it's a high pass filter. Right? We found the transfer function in a similar way using VDR. You can use any circuit laws to find the transfer function. Then a resonating circuit means that the reactive components, reactive elements of the circuit are cancelled out. So the Z is purely resistive, So this happens when this part is 0. So we set, where is it? Where is it? I clicked somewhere, right? Oh yeah, I clicked on this frequency thing. So anyway, resonance results when the imaginary part of the transfer function is 0. So this is the imaginary part. This has to be 0. This means we can use this and we can find omega. And for this one, we can say we call it omega naught resonance, and omega naught is equal to 1 upon under root LC. All right. And this is simply 2 pi f using. The resonance circuit impedance is purely resistive. The supply voltage Vs and current I are in phase. So whenever there is just resistance, voltage and current are in phase. That is, the angle is 0 and power factor is 1. This means we are actually using it at this optimal conditions, getting maximum power. It is also related to somehow from the maximum power transfer from circuit theory. All right. What else? This is just another example, I believe. Oh, the continuation. Series resonance. So the maximum power occurs at Vm. The voltage is Vm. We call it Vm, and the current is Vm upon R. Vm upon R. So we find the voltage at omega naught. Right. So once again, this is the bandwidth, as I mentioned. So let me just come to. So basically, omega 1 and omega 2 are the frequencies at which the power is half the maximum. How do we find it? We set the Z, the impedance equal under root 2 upon R. This is coming from maximum power transfer theorem, this one. So P omega 1, P omega 2 is half of Vm square upon R. Let me go back. The power was half Vm square over R. So half of this is 1 upon 4, and we can find by using this relationship. So we have this equation. We find we just try to find omega, and since this is a quadratic equation, we'll get two values, omega 1 and omega 2. One of them is the lower frequency, and the other one is the high frequency, but this will be around omega naught. It's not possible to have, let's say if you find something which shows omega naught is somewhere here and this is omega 1, omega 2, I don't think this is possible. Right. What else? Yeah. So bandwidth is omega 2 minus omega 1. Quality factor is basically, if you like fine tune your frequency, narrowing down the bandwidth, will get a better quality circuit quality factor will be higher. So bandwidth and quality factor are inversely proportional. Some formulas. So I think, yeah, this one. So if the Q is more than 10, so it's a high Q circuit, and the frequencies are equally, what do we call it, are symmetrically around the resonant frequency and can be approximated as this. Even this is an approximation, right? But you can use it. So here comes the part in which you guys are interested, that how to find the values. So once we have the formulas, I think this is very straightforward. Omega naught is 1 upon root LC. Finding this, then half power frequency also coming from R, L, and C. Omega 1 is this formula. Omega 2 is this one. This part is positive, I believe. I'm not sure. The formula is omega 1. Yeah, omega 1 and omega 2. You can just see that it's negative and this is positive. I don't think there's much difference. So bandwidth is omega 2 minus omega 1, or you can use the other formula, R upon L as well. And the quality factor is omega naught over B. We find Q is 25, which shows that it's a high Q circuit, and we can use B upon 2 on each side of omega naught. So first finding Q. So this one is finding the bandwidth first and then finding the quality factor. Alternatively, you can find Q first, see if it is 25, then you can find omega 1, omega 2 very easily by finding B. You found out that this is 2 kiloradian per second. Once you have 2, you can go like 1 on plus 1 and minus 1, like this. So 2 upon 2 or 2 upon 2 plus 1 and minus 1 will give you, which are the same values as previously. And at omega equal to omega naught, this means this is resonating frequency. So I is Vm upon R. Vm is the maximum voltage or the peak voltage. This is coming from, probably we forgot, it was given in the circuit actually, in the question itself. 20. This is Vm. I didn't mention this yesterday. So this is the maximum voltage that you can get, and we get I Vm upon R, and at omega 1 and omega 2, it will be 0.707 times Vn, or divided by the root 2, as you can see it's again from this figure. Where is it? 0.707. So this is the value of current at omega 1 and at omega 2. All right. Very similarly, parallel resonance. Are you guys following? Any question? Anyone? Any questions so far? Okay. So I'll come to that. I think this is one of the questions that we have in the tutorial. If it is parallel circuit, very similar, almost similar, except we are looking for admittance rather than because it's like duality allows us to use the dual values of the circuit. We can go other way around as well using the same method also. We will still be able to find the same values, but since this one makes it a bit easier. All right, so same way, omega c minus 1 upon omega L equal to 0. Omega naught is 1. So this is the same same as the resonant circuit. I'm clicking here. I'm going to this one, have the same value for series, same value for parallel. All right. Okay. At resonance, the parallel LC combination acts like an open circuit so that the entire current flows through R. So if you go for the RL circuit, this is RL. So this is open circuit and all the current goes through here. So if you go for the previous one, series one, we go to series one. I think we can go from clicking here. Why can't I click? Somehow, okay. Series is mentioned here. Nope. Series. So what do you think the L and C will be acting as at resonance? In parallel, there were like 3 branches and these 2 were acting as open circuit. But for series, what would they be acting as, the L and C? It's very simple, very obvious. Is it that I cannot read your messages or what? There's no message. So R and C will be acting as, guys, please say something. Can you guys hear me? Can you guys see me?
Yes, that's crystal clear.
Okay. So what would L and C be acting as in a series resonant circuit? It's for Rumaisa actually. Okay. Guys, I want to hear from someone from you. This, yeah, it's very simple as that. It will be like short circuit because only then it is possible to have a current flowing through it, right? But for parallel, it will be okay, and all the current flows from the resistor. All right. Jocelyn, can you please make the survey at the end of this lecture, please? Thank you. Okay, and the value of the current in the inductor and capacitor could be much higher than, so you can see Imax, it could be higher than Imax as well, because Q could be more than 1, it could be twice, thrice, or it could be more than that. It is possible. All right. So same values, almost the same value, I think, and same thing, same some like similar formulas again for high Q. It's like plus and minus, and these are the relationships. So you can see that this is same, you know, this is the reciprocal, same, this one is also same, and this one is also same. So very similar. We can find the values for all these things. All right, and then we take a look at a question. It's like, you know, once again using those formulas, simple as that. Q again has a formula, and then it's like much higher than 10, so we can regard it as a high Q circuit, and omega 1 and omega. So what if it's not high Q? Then we have to use a formula for omega 1 and omega 2. These two. And we can find the impedance. So it's purely resistive because the L and C components have been cancelled out. And we can find I naught. We have this V given as 10 sine something T upon 8,000. So we can get the current. Okay. All the current is flowing through R, we just mentioned. So we can find the power is half I naught square R. We have also seen this before in the previous slides. And or we can also find it using Vm upon this as well. Vm is 10 and Vm square is 100. And for omega 1 and omega 2, the power will be half of this power. Half of this power will be, so you can see that there's an extra 1 upon 2 multiplied. All right, any question? Any question, guys? All right, so were you guys able to see my screen?
Yes, doctor.
All right, because it looks like it wasn't sharing anyways. So if we look at the problems I have already given, so considering there are like 3 or 4 types of different types of questions, and 4.16 to be done by everyone. Okay, this, if you can see the table, all the members have to do 4.16. So M1, M2, M3, they will be doing 4.1, 4.6, and 4.11, but 4.16 to be done by all the members. Is that clear? All right. Any particular question you want me to do? Because the good thing is we are using the formulas. So let me just maybe discuss. I won't be doing it because we don't be needing it. Who's messaging?
Question, sir.
Yeah, go ahead.
For question 4.16,
Okay.
you stated that everyone has to do the question.
Yeah.
So do we all have to submit a video solution?
Yeah, of course. You'll be so everyone will of you will be submitting 2 solutions,
Okay,
your
thank you,
own
sir.
and 4.16.
Okay.
Right? Okay. Yes, 2 questions each member. Yes. All right. So let's take a look at some of the questions. Maybe I think this is 4.123 are straightforward. You have okay, maybe not for some of you, but anyways, the thing is that you're given a resistor and inductor for a series circuit. So they all 1, 2, 3 are similar, and you have to find the value of C that will produce a quality factor of 40. So you're given Q, and if you look at the formula, we have Q in terms of 1 upon omega naught RC. So this is one way to look at it. Then where is it? Questions. Yeah. What else? Quality factor of 40. So from one of them, from this one, you can get omega naught. You're given Q, you're given L, and you're given R. You can find omega naught, and then with this omega naught here and R from the same one with the same Q, you can find C. Right? So once you have C, you can find omega 1 and omega 2. Since Q is very high, we can use B upon 2 to find omega 1 and omega 2. But first we have to find B. B we can find out from omega naught upon Q. We know we have omega naught, we have the Q. So we have the B. Once we have the B, we can use this one to find omega 1 and omega 2 because Q is greater than or equal to 10. Or why is it like this? Display settings, is it? Duplicate slideshow. Okay. So very easily we can find out all the values. So 4.123 are pretty straightforward. I don't think I have to do it for you guys. Then second one is RLC network has R 2 kilo ohm, L 40, and C this. Calculate the impedance at resonance at 1/4, 1/2, twice, and 4 times the resonant frequency. So first of all, find the impedance. Find the impedance means like same as if it's a series, is R plus J XL plus 1 upon J omega C. I would wish, can I cannot use this as a highlighter, this is a pen. Oh, I have to switch to the other device. Hold on. Let me come from the device. Okay. So Z is actually R plus J omega L plus 1 upon J omega C. Okay. So how do you propose to proceed? First of all, use the resonance condition. At resonance condition, this has to be 0. J omega L minus J upon omega C will be equal to 0. Or you can use the formula for omega naught as well. But this is one condition. Omega L minus 1 upon omega C equal to 0. If you don't remember the formula, you can use these as your reference. But let me just show you the formula as well. It was 1 upon under root LC. So we have L, we have C, we can find omega naught and put the value of omega naught in here and in here to get Z at omega naught. And then they're asking you to find at 1/4, 1/2, twice, and 4 times the resonance frequency. So once you have found omega naught, find at omega naught upon 2, omega naught upon 4, 2 omega naught, and 4 omega naught. Is that clear? Is that clear, guys? Is it okay? Yes, no?
Yes, sir. Yes, sir.
Okay. Thank you. Here. All right. So this was about the second batch of questions. Then 4.6, 4.6. Okay. Now we have a circuit consisting. I'm reading 4.7, which is the 7, 8, and 9. A circuit consisting of a coil with inductance 20 millihenry. So inductance and resistance is given in series with a capacitor, and a generator with an RMS voltage is given. Find the capacitance that will cause the circuit in resonance. Okay, so once again, can you guys see this? Yes. Resonance at 15 kilohertz. So we are given F. We can relate F omega 2 pi F. So omega naught. We can find omega naught. Once we find omega naught, we can find C. Oh, this is part. Hold on. The value capacitance will cause the circuit to be in resonance. Yes. So the resonating frequency is given. This is basically this. So we get omega naught, and using omega naught, we can use the formula for omega naught with C, which is again this one. This is a parallel series here. This one. And once we have C, we can find the value. That's it. The current through the coil. So to find the current, once we have C, L, and R, we can put them in the circuit and we can find the current. And of course, we'll see that these will be cancelled and only R is appearing. So we can find the current, and the Q is like some of the formulas that we have seen. So I couldn't find difficult questions for this particular topic, but I hope it will still be challenging enough to at least raise some understanding. All right, I have changed some values somewhere. I believe that this is 10 and this is 20. So I have changed some values. Then the next batch is design a series RLC circuit with B equal 20 radian per second. Omega naught 1100. Find the circuit's Q. Let R equal 20. Right. So if we look at this one, we are given 20 as R, and B is also given omega naught. Okay, omega naught is given. Okay, fine. If omega naught is given, if you remember, B equal omega naught upon Q. All right. So let me take which one? Probably anyone. This one. I'm taking this one because it's easier. So Q is 1200 divided by 10. So Q is 120. Remember, Q has no unit because it's a ratio. So once we have Q, we have to find L and C. And if we remember the formula for quality factor, it's either omega naught L upon R or 1 upon omega naught RC. So once we have Q, we can find L and we can find C because omega naught is known and R is known. We can find C. So this is kind of a designing part in which you can find the values. Okay, by the way, sometimes when it's about designing, you sometimes take one value, like let's say suppose this is not given, this 10 or this 30 is not given, and you're asked to design the value, design the values. What you can do is assume a value. Let's say assume R is equal to 10 or 20 or 100 kilo ohm or something, and then find based on that. This is also designing. You know, this is just like you are starting to make something and values are interdependent to each other. You can see that all the values are interdependent. So you need a starting point. So if suppose this is not given, if this is not given, then you can assume this value starting from, let's say R is equal to 100 kilo ohm or 100 ohm or something. This is also a way of designing. And if you remember from circuit theory also, while working with op amps, you were designing the particular adder or subtractor or differentiator or something based on setting the value of R. So this is, so suppose if this is not given, you can assume R is equal to 100 and then proceed accordingly. Right? Is that clear? right, there is no question from you guys. Okay, I assume that this is clear. Then 12, 13, 14, 15. This is similar. This is designing RLC circuit in parallel, very similar. And then 16, I'll let you guys do it on your own. Okay, again, it's not that difficult. Any question?
Yes, I have a question.
Yes, Asfer.
For the designing circuits,
Uh-huh.
do we have to draw the circuits?
Actually, like drawing is like series or parallel. You can draw it. Yes, you can draw it for sure because it's already given. It is series circuit. So just put the source R, L, and C. That's it. If it's parallel, like two, like three branches, you can draw it. But the designing is not like art design. Not this is not art design. This is like values. Whenever we say design, we say that we are designing a circuit or a system parameters, in which case here the R and L and C, these values, uh, we designed it to so that we achieve a desired output. It is given that the desired frequency is 1200 or whatever. So we have this is something from control system as well. For control systems, we are having in mind that this is my desired output, and I change the parameters inside the system to achieve that particular output. Okay, so but in this case, designing doesn't mean like you have to like put, it's already given series circuit or parallel circuit, right?
Okay, thank you, sir.
Okay, anyone else? Any question?
No, sir.
All right, then we break from here to your groups. I think this time you can finish off a bit faster than usual because the questions are not that difficult and I've already instructed you. So you can break into groups, and once you're done, let me know. Okay?
Okay, sir.
Okay. Thank you. Please mark your attendance. Those who have not marked the attendance, I still see that. How many of you? Only 15 responses so far. Only 15. So please mark your attendance. I have how many students? Like almost everyone is here. So please mark your attendance. All right. I'll see you in maybe 10 minutes.
Yes, sir.